Hello, my name is Alejandro Ojeda, and today I'm going to talk about Lab 2 motion of a foreign object, or in my case, a line. The intro key concepts would be that we need to know about Newton's second law, which is the net force is equal to the change in momentum divided by the change of time. Then we need to know that the velocity formula is final velocity is equal to initial velocity plus net force times change of time divided by mass, and the position formula would be the final position, is equal to initial position plus the average velocity times the change of time. Then we also need to know the force of gravity, which is vector 0, comma negative mass times g constant. At g constant, we derive it from mass 1 times g constant is equal to universal g constant times mass 1 times mass 2 divided by the magnitude of r raised to the power of 2, m2 being the mass of the earth and r being the radius of the earth. And as a result, we'll get 9.8 meters per second as our gravity constant. So drag is against the direction of gravity in this scenario. So then we will use the formula, the force of drag be 0, comma b, which will be the drag force coefficient, times the magnitude of velocity raised to the power of 2. And additionally, we need to know that the system is lime, and the lime and the surrounding will be everything else. And therefore our goals will be to observe the position over time of the object, in my case the lime, and compare the motion with glow script and tracker with and without the drag force in glow script. And the main assumption is that there's only one motion in with the y-axis. Here's a video of me doing the experiment. Amazing. Then we go to tracker analysis. Mainly, we have to see the changing time is 0.1 seconds. The initial position was 1.5 meters in the y-axis. Initial velocity was 0 meters per second, both x and y-axis, and the final positions are the same, 0 meters in the x and y-axis. And the time of observation was around 1 second. So this would be the code that we use for the model without the drag force. Main things to consider here is that the coefficient for drag is 0, and then we use the force of gravity as the force, the net force for this experiment, and then implement net force in the velocity of the ball. And then for the drag code, we have to also consider that both have the initial ball position. The only difference now is that the drag force now has a drag force coefficient, meaning that there's two forces now: the force of gravity and the force of drag, which is and then we use the force of drag will be equal to the formula that we used previously, and then for the net force will be the sum of the force of gravity plus the force of drag. So P will be how the arrows were coded, and later this is how it will look like at the end of the day. And we know that the model with no drag force travels more than the model with drag force because it is not being slowed down as much as the model with drag force. Then for discussion, we also know that all models started with similar change in position, but we have to consider that the observed model started actually falling at 0.1 second, meaning that it took about 0.9 seconds to touch the floor, and the predicted without drag force model took 0.535 seconds, while the predicted with drag took 0.557. So there's possible sources of error, mainly being the placing initial position of line in the tracker, incorrect tracking of line due to video distortion, and inaccuracy for determining drag coefficient. So in this case, the question for what does it mean is that what does it mean when it reaches terminal velocity, meaning that force gravity and force drag are equal. That means that F net is equal to 0, and therefore velocity becomes constant. That will be with drag force, because then velocity becomes constant. And then what if is when we put initial velocity to the system with drag force. After coding it, we found out that if we initial velocity, it would be 0.3 meters per second faster compared to when it was without initial velocity. Thank you so much.